Hi, my name is Max von Hippel, and today I'm going to be presenting automated attack synthesis by extracting finite state machines from protocol specification documents. This work was a collaboration with Maria Lenore Pacheco at Purdue, who recently graduated, her advisor, Dan Goldwasser, also at Purdue, another student from my lab, Ben Weintraub, and our joint advisor, Cristina Nita-Rotaru. Today we're going to be talking about the internet. The internet runs on protocols, and the idea is that if two computers on a network are running the same protocol, this gives them a shared language by which they can communicate. And examples of protocols include TCP, UDP, DCCP, etc. I have pictured here the ARPA network in December 1969, arguably the original internet. At the time, there were 4 computers networked together, but the internet has grown a little bit since this picture was drawn. Each protocol peer on the internet runs an instance of the program implementing the protocol they're using to communicate, and this is usually described with a formalism that we call a finite state machine. A finite state machine is a directed graph where the nodes represent states in the protocol logic, and transitions or edges are changes in state. These often correspond with some event like sending or receiving a message or having a timeout. In general, we can find attacks against vulnerabilities in or flaws in these types of protocols by analyzing their finite state machines. So we'd like the finite state machine to have kind of enough resolution that by analyzing it, we can understand whether or not the protocol achieves its intended purpose, at least abstractly. In my lab, also Ben's lab at Northeastern under Cristina Nita-Rotaru, we specialize in building automated attack discovery tools. So what we do as a group is that we build tools which usually take a finite state machine model as an input, and they're guided by that model to find an attack against a protocol. Perhaps using formal methods such as Korg, which is a tool I'll be using today and which I presented at SafeComp in 2020 that I authored, or maybe not using formal methods like Snake or TC-Pwn, which were done by a previous member of our lab, Samuel Giro, and which won Best Paper Awards. But such tools require a protocol finite state machine in order to guide the search for an attack. So the question becomes, where can we find one of these state machines? And that's something we'll be working on today in this presentation. So one potential source of information from which we might find the data we need to construct a finite state machine would be what's called a request for comments document, or RFC. RFCs provide specifications and organizational notes for the internet. They're produced by the Internet Engineering Task Force, which is associated with the United States government, and they describe the main internet protocols in prose. Here I have pictured a screenshot from the DCCP RFC, and you can see what I mean when I say prose. It's plain English documentation. So this is not, in my dream we'd have like COC or AGDA or something, but that's not what we actually have. We have English documentation of how the protocol works. An alternative place to look for information would be in an actual implementation. So I might look at some implementation in a language like C or C++ or Go and try to extract a finite state machine from this. Such implementations are manually derived from request for comments documents, but they don't necessarily contain all the information from an RFC because there might be optional functionality that they don't contain. And they contain some information not found in the RFC, such as what you might call folklore knowledge or domain expertise. So we have 2 sources of information where we might look to find a protocol FSM in order to use one of our tools to study the FSM and find flaws. And the first would be the code, and there's actually quite a lot of work that does this. In fact, I imagine there are probably numerous papers at this conference this week that do this type of thing. And such papers might do static or dynamic analysis. They might run the code and study the traces, or do any number of other things. So that's a very well-studied and very interesting problem. But another problem would be to extract a finite state machine directly from the specification document, which might be an RFC or something else. And to the best of our knowledge, nobody prior to this work has ever fully extracted a finite state machine of a protocol, or even attempted to do so really, from just a protocol specification document in plain English. So that's what we're going to try and do today. So we'll ask 2 questions, and we'll answer both affirmatively. And the first question is, can we automatically extract a protocol finite state machine from just its English language prose specification document, in our case, a request for comments document? And the second question is, when we extract this FSM, we kind of want to know, like, is it correct somehow? And sort of it's difficult to define what this means. So for us, it's going to mean, is the FSM good enough to do something useful? And we believe something useful means using it for a real-world application. Our application will be attack synthesis. But we claim that any number of other applications might work as well. We face numerous challenges when working on this. And the first challenge is that there really is no one-to-one mapping between text and what we call canonical FSM, or in other words, the FSM that an expert would write by hand based off a reading of the RFC. In fact, when such FSMs are created, they require a lot of domain expertise and careful human reading because the English language text is inherently ambiguous. The second problem is that RFCs specifically will contain many omissions, mistakes, and ambiguities. Here we have a quote where, if you read the quote carefully, it would imply the existence of a transition from part open to open upon receipt of a DCCP close message, but of course there is no such transition. So this is an English language ambiguity. It's made clear to the expert when they read the document, but it is frankly an ambiguity in the text. And such ambiguities and omissions exist in many RFCs in our experience. Third, off-the-shelf natural language processing techniques are simply not suitable. Generally speaking, such techniques are trained on newswire text or other types of, perhaps you might say, more natural language, but we really need to have something that knows how to read technical language, and technical language is inherently different from natural language. And so we can't really use something totally off the shelf and achieve good results. Fourth and finally, there's a lot of variation in the language and structure of different RFC documents. They're authored by different people using different styles. There's no kind of standardized way to write an RFC. And so something that works really well on one RFC might not work that well on another. And this creates another challenge for us. We take a 4-step approach. The first step is to create a technical language embedding, which captures various interesting or important features of the language that we want to describe. And we'll talk about this more subsequently. The second step is to read the RFC and extract a representation of it using our technical language embedding, using a zero-shot approach, which means that when we apply our approach to some test data, that test data was never observed at the training time. So it's this kind of no cheating in some sense. But this extracted intermediary representation, we're not done yet. It doesn't actually contain a model. It just contains information in some sense about how to read the document. So now it's time to read the document. We do so, and we extract a finite state machine from the intermediary representation. Fourth and finally, we have a finite state machine. We want to know, is it good for anything? So we do something with it, namely attack synthesis. And I'll be going over each of these steps in more detail. So step one is learning the technical language embedding. We use a contextualized representation called BERT. And the basic concept is that the meaning of a word is based not only off its kind of strict definition, but also its context. In this case, the word reset means a different thing depending on the words that surround it. So BERT takes into account not just the word, but also the context it resides in. We train our model on approximately 9,000 documents and approximately 500 million words. So an example of what our embedding might look like is maybe useful or more useful than just purely technical statements about it. So let's look at this example text. Here we have some text from the DCCP RFC, and we want to take this and annotate it in some richer way so we can use it for something useful. We're going to do so with a grammar. Our grammar will consist, first of all, of definition tags, which define states, events, etc. Second, we'll have reference tags, which track references to things that we defined previously using our definition tags. Third, we'll have state machine tags. These are arguably the most important tags in our grammar. They describe, for instance, the transitions within a state machine. Fourth and finally, we have control flow tags, which in some sense capture if, then, else type structure in the document itself, or kind of the control flow of the language of the document. So here's that quote from before, but now structured according to our XML. On the outermost layer, we have a control block, which is going to scope our search. It says essentially all the important logic for this thing you're trying to extract is within this chunk of text. Second, we have a transition block, which contains the source state, where the transition begins, and the target state, where the transition goes to. Third, we have the event, which triggers the transition, which in this case is the receipt of the message with identifier 2, meaning when we had the def state for it, its ID was 2. So we need a way to go from plain text to something that looks like this. We have two approaches to do this. The first is a linear conditional random fields model, or linear CRF. The linear CRF first splits the text into chunks. It then extracts features. These features are things like capitalization patterns, the existence of different mathematical formulae, et cetera. And then it feeds those feature vectors into a linear CRF model. I'm not going to get into the model in detail, but it builds on the Markovian assumption that the next state is entirely predicated on the previous state. We also try a neural equivalent of the linear CRF model, so something that is very morally similar to the linear CRF, but is based off a neural network architecture, and we call that neural CRF. We evaluate on a number of RFCs, and we find that both our linear CRF and neural CRF models do a better job extracting intermediary representation than a purely heuristic rule-based method, which is what we'd expect. We also find that the neural CRF model does slightly better than the linear one, and we'll see in general in this presentation that our neural model slightly outperforms our linear model. So we've now explained how, to some extent, we generate this intermediary representation, this structured XML that tells you how to read the document. Now we want to do something interesting with it. And the first step is going to be to take this and read it in order to get a state machine, to get states and transitions like this one. So we use a purely heuristic extraction algorithm, and our extraction algorithm was really designed with the TCP and DCCP RFCs in mind, although it should generalize to other RFC documents. Essentially, we search lower in the XML for targets, higher for sources, and we have some smart ways to do things like handle set complement in sentences. And in the end, we may find quite a few transitions, and then we use some heuristics to filter out the ones that we think are perhaps noise. And these are just based off our experience working with those RFCs. So we evaluate on the transmission control protocol, and we introduce this idea of a gold intermediary representation, which is one where we simply annotate the document by hand. So in theory, the annotations are perfect, and we compare that to what we get with the linear CRF and neural CRF models. We have this very interesting result with TCP that although the intermediary representations we get from the linear and neural models differ, the actual extracted FSMs are going to be identical, which is kind of funny. We define a transition as being approximately correct if the start and end states are correct and at least one event is correct. And we find that we get most of the transitions approximately correct, but there's quite a few incorrect transitions in addition in the cases of the linear CRF and neural CRF. And our results with DCCP are reasonably similar. In contrast with gold, very few transitions are incorrect, which is what you'd expect. We'd like to know, though, why do we get so many incorrect transitions, right? I mean, this is sort of a fundamental limitation. So why does this happen? So with the gold intermediary representation, all the incorrectness is due to omissions or ambiguities in the text, which makes sense because theoretically the annotations are perfect. However, with the linear CRF with rules and neural CRF with rules, this substantial majority of errors are caused by prediction errors. The DCCP results are similar, but they also contain some extraction error and post-processing error. Finally, we have an extracted finite state machine, and now we're going to do something useful with it. So we've shown you that we get a machine. I've said that it may have some errors in it, and you might be thinking, well, with all those errors, can you still do something with it? And the answer is going to be yes, and now that's what we'll show. So as our representative application, we use Korg, which is an automated attack synthesis tool that I authored and published at SafeComp in 2020. Korg takes it as input the extracted finite state machine, which we just went over, as well as a linear temporal logic property that we write manually based off a close reading of the RFC document. I wrote these properties with Ben Weintraub, which is one of the other authors on this project. Those properties plus the model are fed to Korg. Korg then generates essentially a system capturing two protocol peers communicating over a vulnerable channel. And the channel has a sort of non-deterministic vulnerability. It's sort of underspecified. And under some assumptions, which are given in the paper, it asks the spin model checker, will this system satisfy the correctness properties? In the likely event that the system does not satisfy the correctness properties, the spin model checker will find a counterexample, which is a sequence of events in which one of the properties fails. It hands it back to Korg. Korg then generates an attacker program which simply replays that counterexample. It's quite simple. If you provide Korg with a canonical FSM, one that you wrote by hand, it will test the attack to see if it works. But in principle, if you're using our technique, you probably don't have that. We do two case studies, TCP and DCCP. For time, we'll only mention TCP. For TCP, we have 4 properties. The first 3 come from my Korg paper, the SafeComp paper in 2020, and the fourth Ben Weintraub wrote based off of a close reading of the request for comments document. And we have a canonical FSM, which I wrote. It's very similar to the one that I used in the Korg paper, but with some slight modifications to better support our setup for this paper. Okay, so in terms of results, with TCP, only the first property turns out to be useful with any of our extracted FSMs for generating attacks, and we discuss why in the paper. We find very few attacks, but all of them are confirmed against a canonical FSM, meaning that they are true positives, they actually work. And because we have identical FSMs with the linear and neural models for TCP, we get identical results. In the case of DCCP, the results are somewhat different. Across the gold, linear, and neural CRF models, we find attacks with numerous properties, but there's 2 things that are interesting here. The first is that we find many more attacks with DCCP than we do with TCP, and yet many of those attacks are false positives. So you'll see that many of them are called unconfirmed, so they don't actually work against a canonical state machine. The second thing that's interesting is that we actually find more attacks using linear and neural than we do using gold, which is quite interesting. And this seems to be kind of a complicated signal to noise trade-off type of thing, and we discuss this more in the paper. I'm also happy to take questions about it. So you may ask, like, what are these attacks, right? You say you find attacks. What do those attacks look like? One example for TCP would be injecting a single acknowledgement into one of the peers during the establishment routine, which can potentially cause a desynchronization, although it's not guaranteed to. It depends on some non-deterministic decisions. This is a reproduction of a result from the Korg paper. In the case of DCCP, an example attack would be one elaborately spoofs each peer to guide the other into closed rec. There's no closed rec state because there's no active-active teardown in DCCP, so this is an incorrect behavior. And we define an attack as something that induces an incorrect behavior. And we actually find multiple variations on this theme, which is because we use a model checker, and the model checker is kind of based off graph search, so it's going to find maybe multiple paths to similar outcomes. So we find that we might generate half a dozen attacks that are quite similar, but programmatically different, but do the same thing. So in conclusion, we asked 2 questions. Could we extract FSMs from RFCs, and could we do anything useful with them? The answer was yes, we could extract FSMs, but they might have some errors, so we call them partial FSMs. And yes, we could do something useful with them, but depending on the protocol, we may have more or less success in terms of generating attacks. However, we confirm many of our attacks using a handwritten canonical FSM. All of our code, a Docker file to reproduce every single one of our results, detailed documentation, extensive tutorial on using our code, and detailed error analysis are all available on GitHub, and more results are in the paper. And with that, I'll take any questions. Thank you very much.
Awesome, thank you very much, Max. So I just got a message from our program chairs that we should try our best to conclude this session by the original planned end time, because the online platform will kill their connection at 10:50 a.m. sharp. You know, this is not what we would expect in 2022, but here we are. So what can we do? Because of that, we will need to keep our question and answer sessions kind of short. So if you have questions, please line up behind the microphone. I will take maybe 2 questions from on-site and then 2 from the online. So since no one's there, I'm going to start from the online questions. There are a lot, by the way. You know, you press at work. This is why people are asking questions. So the first one, can you please provide some insights in terms of why the linear and neural FSMs are identical?
Yeah, I think it has to do with our heuristic extraction algorithm. So I think that essentially the differences in the intermediary representations were things that are not meaningful in terms of our extraction algorithm. And by the way, for people watching this, I think that our extraction algorithm is one of the easiest things to improve on for what we did. So I would encourage anybody who wants to work on this type of thing to think about maybe how to improve on the extraction algorithm.
Awesome, thank you. No questions from on-site? Okay, so the next question. Does your research also analyze figures and or diagrams in the specifications?
No, that's a great question. We discussed it. It's actually an interesting problem in NLP to kind of richly understand what diagrams mean. At one point, I played around with a little hacky script that would extract an FSM from an ASCII diagram, but it's hard to generalize such a thing in a really scientific manner, especially when you can have many different types of diagrams like control flow charts and stuff like this. But it is an interesting problem for sure.
Awesome, fancy. No more questions from on-site? 3, 2, 1. Awesome. I'm sorry to people who are asking questions on Hopin. So if you can you please attend to those questions afterwards?
Absolutely. Thank you very much.
Thank you very much.